So, hey everyone, today I'm going to talk to you about new insights into old data and re-evaluating the epithermal gold potential of the Coromandel Peninsula using a machine learning technique. So, first I'll go through the background, the geology and mineralisation, talk about the data that was used in the modelling, and then the different mineral potential mapping techniques that were used, and then some insights and conclusions into what re-evaluating the data has actually told us. So why bother looking at old data again? Well, obviously the social license to operate is becoming more of a challenge with society. And also on top of that, on-ground exploration is expensive and can impact the environment, both of which are important for any exploration program these days. So what we're looking to learn is whether reanalyzing old data using new techniques can tell us anything new about the mineral system and the key targeting criteria that we use for our exploration for that mineral system, and whether new techniques can provide new exploration targets that hadn't previously been noted. So the Coromandel case study comes from a data compilation and mineral potential mapping study that CanX undertook in 2012 using publicly available geoscience data. And at the time of the data compilation in 2012, a data-driven weights of evidence mineral potential map was created for the epithermal gold-silver mineral system using this data. However, in 2012, we've reanalyzed the maps produced in 2012 using the random forest machine learning technique. So the mineralisation, we're looking at low sulfidation epithermal gold mineralisation, which is related to the Miocene-Pliocene volcanism in the Coromandel volcanic zone. It is typically andesite hosted and related to extensional faults and fractures. And the mineralisation also typically shows a zoned hydrothermal alteration signature. So when we're looking at doing mineral potential mapping, we used a mineral systems based approach, which involves translating the fundamental ideas about the processes involved in the formation of a mineral system to mappable targeting criteria from which we can map spatial proxies from our available GIS data. And all of the processes, so source, transport, trap, and deposition and preservation processes, must occur for the mineralisation to form. It's only the proxies that are used to represent these processes that change between the different mineral systems. So the data that we used in the study was compiled in 2012 from public sources, which you can see a list of here, mostly coming from GNS. And in 2012, when the data was compiled, a comprehensive quality control process was undertaken, which looked at trying to fix up any errors that were noted in the data, so location accuracy or any errors in the attributes that were found. And then this data was integrated into a data-driven mineral potential mapping study. So data-driven mineral potential mapping looks at the spatial relationship between predictive maps and training data, where predictive maps are spatial proxies that represent the different processes for our mineral system. And training data get represented by known mineral occurrences that relate to the mineral system. So for our epithermal gold system, we're looking at trying to use epithermal gold training points for our modelling. So different data-driven methods use different approaches for establishing and quantifying this spatial relationship. So weights of evidence is an empirical statistical approach that uses Bayesian statistics, and random forests are an ensemble machine learning approach. So both of these methods were used by CanX for the mineral potential mapping because they allow some degree of user intervention to ensure that during the modelling process, the results actually make geological sense in the context of the mineral system that's being modelled. So we don't end up with some nonsense results. They aren't black box type approaches. They do allow a review of the outputs at different stages of the modelling. So the workflow used, we start off with our original data. Obviously, this is not a comprehensive list, but it is commonly available and commonly used data for mineral potential mapping. So from our data, we mapped spatial proxies, and in this particular study, 71 spatial proxies were developed for our epithermal gold mineral system in the Coromandel. These here are coloured up by their relationship to the mineral system's processes, so source, transport, trap, and deposition. And from these spatial proxies, we can then train our models. So the weights of evidence model looks at the correlation between a set of known epithermal gold occurrences and the different spatial proxies, predictive maps. So each the statistics help us to determine the thresholds, so distance, buffers, density thresholds, etc. And the thresholds have to be statistically valid. They need to be geologically meaningful in the context of the mineral system that's being modelled, and they need to be practically useful in terms of helping us to reduce our exploration search space. So from the 71 predictive maps that were tested, 33 of these produced a valid statistical output from the weights of evidence. And from these 33 maps, 9 were selected for input into the weights of evidence model in order to try and limit some statistical dependencies, which I'll go into in the next slide. So from here, this was undertaken in 2012, but from here, we then took the maps that were produced during the weights of evidence analysis and put them into the random forest machine learning method. So random forests uses some additional non-deposit training points for the modelling process. So not just our known epithermal gold deposits, we need to pick some locations where we're fairly confident that there is no epithermal gold deposit. So the input maps into the random forest are the same statistically valid predictive maps that came out of the weights of evidence analysis. And we tested 2 different random forest models, one using the same 9 input maps as the weights of evidence model, and a second model which used all 33 valid predictive maps from the weights of evidence. So you can see how they relate here. And once the training has been undertaken for the different mineral potential mapping techniques, we then need to classify our outputs. So our weights of evidence map gets classified into a prospective and unprospective area based on its post probability value, which is its prospectivity based on the statistics. And then the random forests gets classified into prospective and unprospective area based on the deposit and non-deposit training data. And that's similar for both methods, both of the random forest models. It's just that the number of input maps varies for the 2 models. And then a validation step is undertaken and looks at how well the model predicts a separate subset of epithermal gold occurrences that didn't get used as training data, so that we're not using exactly the same data to both train and validate our models. So weights of evidence, this is a data-driven method that quantifies the spatial association between our set of known mineral occurrences and predictive maps, and looks at whether a deposit or a training point is present or absent given the presence or absence of a predictive map pattern. So in other words, is a felsic volcanic present or absent? And these statistics take into consideration the amount of area covered by the predictive map patterns, which can be really important, because if the predictive map pattern covers 90% of our study area, is it a particularly useful targeting criteria, or are you better off just throwing your data to map? However, the weights of evidence approach, one of the challenges with this is that it assumes conditional independence, so that all of the input maps that go into our final mineral potential map are statistically independent of each other. However, when we're modelling a mineral system, this is rarely, if ever, the case, because the mineral system's processes are generally all interrelated. So looking at the weights of evidence results, the map here is classified into prospective and unprospective area, and we can see the epithermal gold training points plotted over the top. And in the table here, we can see the different spatial variables or predictive maps that have gone into our mineral potential map and how they relate to the different mineral systems processes. The variable ranks here are based on the statistics, and so the maps that have the strongest correlation have a higher variable rank. So what we can see from our prospectivity map or a mineral potential map here is that prospective area covers about 16% of our overall Coromandel study area. And the accuracy, which is how well it predicts the location of our validation data, we get an accuracy of about 90%. And the variable ranks here show that the controls on the mineralisation are indicated to be the alteration and the structural controls. The andesite is important, obviously, for the epithermal mineral system. However, as I was saying before, the statistics in the weights of evidence method take into consideration the amount of area covered by a particular predictive map pattern. And the andesite does cover quite a lot of area compared to the size of the study area, which reduces the strength of its correlation with the training data. But the modelling does emphasise that the extensional structures are important for the transport of our hydrothermal fluids in the system. Then moving on to the random forest-based approach. So random forest is a decision tree algorithm where the aim is to decide whether a deposit is present or absent, given the presence or absence of a particular map feature or characteristic. So it uses the known deposit locations, so the same training data as our weights of evidence model. However, it also requires a set of non-deposit locations to assist with the training and the classification. So it goes through these decision trees, and for each random predictive map in the tree, it tries to decide whether a deposit is present or absent, given the presence or absence of the map pattern in that predictive map. And then it aggregates all of these decision tree votes together to reclassify the entire set of predictive maps into the required number of target classes, which in this case is 2. And the target classes are deposit or non-deposit or prospective and unprospective. Now, random forests aren't constrained by the same conditional independence issue that the weights of evidence method has. So we are able to more effectively utilise all of the available data rather than just a small subset. So we can use all 33 valid predictive maps rather than just the 9 that were selected to go into the weights of evidence model. But just for comparison purposes, we did run the random forest with just the same 9 predictive maps, and we can see on our mineral potential map here, we have the epithermal gold training points, but I've also plotted up here the non-deposit training points that were used in training and classifying the random forests. So again, the variable ranks here, they're based on a statistic called variable importance, which comes out of training the random forest model. And we can see that the prospective area here is about 22%, which is quite a bit higher than the 16% that we got for the weights of evidence model. And its accuracy, so how well does it predict our validation data? We get an accuracy of 96% compared to the 90% or so that we got for the weights of evidence. However, what we see from our variable ranks here is that the geochemistry ranks relatively poorly, and the faults also get a slightly lower variable rank, which is indicating that the structural controls might be local rather than regional. But it does emphasize the lithological and the alteration controls. We can see here that the variable rank for the andesite is rank number 1. And this is because, unlike the weights of evidence model, the random forest doesn't consider the amount of area covered by that particular predictive map pattern. And then the results for the 33 map model. Again, we see the prospective area is about 19.6%. So it falls in the middle between the weights of evidence model and the 9 map random forest model. The accuracy is the best out of the 3 at predicting the location of our validation data. And then the variable ranks here, instead of going from 1 to 9, they go from 1 to 33. Because there's 33 input maps. I can't list them all here. So just for comparison purposes, I'm showing the same 9. But the random forest model using the 33 input maps is emphasizing the lithological and the alteration controls as well, but not shown in this table here. It's also showing quite a strong stratigraphic control. So that's suggesting that it's not necessarily just the andesite that is important. It is also which particular andesitic units they are. So what's changed between the three models? So on the left, we've got the weights of evidence model. In the middle, we've got the 9-map random forest model. And on the right, we've got the 33-map random forest model. And I'm just circling here where some of the differences are. So in the weights of evidence model, we've got a bit of prospective area over here that doesn't show up in the random forest models. In the random forest models, we've got some prospective area up on Great Barrier Island in a few other locations down the Coromandel Peninsula that are not showing up as prospective in the other two models. So we're getting the most prospective area in the 9-map random forest model. And you can see that it's not just an extension of the existing prospective area. There are some completely new areas that are coming up that are not showing up in the other two maps. So where to next? We looked at just straightforward combining the three mineral potential maps that were produced from the weights of evidence and the random forests to show areas that are consistently being highlighted as prospective. So on this map, the unprospective area is where none of the mineral potential maps were prospective. Weakly prospective, there was 1. Moderately prospective, there were 2. And highly prospective, all 3 of the mineral potential maps were prospective. And if we then decide to overlay the DOC public conservation land map and the current tenement situation, it shows that there is still highly prospective ground in non-conservation areas and that don't have current tenements over the top of them. So obviously there is more than one reason for not being able to explore in some of these areas, but we just figured that the DOC public conservation land map was a good first pass assessment. So zooming into a couple of areas around existing mining districts, we can see here the amount of prospective area around Hauraki and Martha Hill. And again, plotting up the DOC public conservation land map and the current tenement situation, we can see that there are still some highly prospective areas where we might possibly be able to do some exploration for our epithermal gold mineral system. So insights, basically we can look at the results from the random forest mineral potential mapping and see whether we can reconsider what are effective exploration targeting criteria for the epithermal gold mineralisation. So the results were suggesting that stratigraphy is important and not just lithology, so it's not just the andesite, but which particular andesites, looking at the local scale structural controls rather than just the regional scale structures. But it's also suggesting that the stream sediment geochemistry was not a particularly effective targeting criteria, despite having a pretty good sample distribution across the study area. And it has shown that there are new exploration targets that were highlighted from the random forest models that were not just an extension of the existing prospective area. So they might represent new exploration opportunities. However, out of the 3 models, it did show that the weights of evidence approach was still the most useful for narrowing down the amount of prospective area, so narrowing down the exploration search space. But all of this being said, new data is always welcome and is still going to be required for more advanced exploration projects where we're looking to do some kind of drill targeting, for example. Thank you.